All right. So practicing on polar graphing. However, I want people to be aware of, let me bring it over. I found this, and I'm saying this specifically for the recording. I'm going to try to show you the link to this. Actually, well, that's a very long link, but I'll share it with the class. You can look at this Cartesian graph. And I'm still trying to figure out how to change this so I can just let everyone in. But basically, you can look at the Cartesian graph and you can look at the polar graph and see how this vertical length that you're used to understanding translates into this radial coming out of the origin, and watch it turn. So basically, when we look at our polar graph of cosine x, we can have our angle go from 0 to pi over 2, and we can see the translation of the y value turning into the r. But instead of the x-axis creating a whole nother dimension, we are looking, can I now get that back? There it is. We're looking at almost taking the x-axis and bunching it up into one point and then letting it all flail out. That is a way that I've thought about what it means to translate Cartesian into polar, is to literally just pinch the entire x-axis to a point and let all of these come out at different angles, and those angles match up the x that you're on. Does that kind of help some of you a bit? Okay. So again, you can play with this. Let me put that up again. Copy. And let me see if that. So if you just came in, here is the link. And I will, again, post it with the recording that I have here because it is really, really, really beneficial. This has a whole bunch of things that you can do to just try and get to learn polar graphing from more of a basic level. So let's look at just, can you create your own polar graphs? So let's do r equals, I'll just throw some stuff around. Okay. So if you were given this and you were asked to draw the polar graph, you could start with thinking of r as being y and the theta as being x, and just draw what you know this graph looks like. So you've got your cosine graph stretched by 10, so it has that amplitude of 10, which would be looking like this, and then up 5 units. So by moving it up 5 units, the sinusoidal axis of the center is now 5, and then we go all the way up to 15 and up to -5. And then we draw our cosine graph. Wee, 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 and wee. And we know that that's 2 pi. This gives us points that we can literally plot. So I'm going to put in just these particular angles that we're really familiar with. We're familiar with 0, pi over 2 pi, 3 pi over 2, and 2 pi. We know exactly where they're landing. So what we can do is we can draw a point plotting on on the positive x-axis, the positive y-axis, the negative x-axis, and the negative y-axis by just simply looking at these points. So angle 0 is working with the positive x-axis, and this says I'm out at 15 units at angle 0. At angle pi over 2, I know that angle pi over 2 is located right here. And for angle pi over 2, my y value on the graph of the Cartesian is 5. That makes the r 5, which I'm going to approxiplot halfway decent. Then when I get to pi, that is down at -5. So I'm actually needing to look at this being 0, this being the positive side of a line, and this being the negative side of that same line. -5, when I'm at angle pi, is actually 5 units in the negative direction. Now, you feel like putting a -5, but when you plot your polar points, you keep them positive at all times because it's just representing the positive radius. When you go to plot the point, you just know to plot it at the +5 on the opposite side of your 0. Then when we hit 3 pi over 2, we are back to 5 again. And then at 2 pi, we go all the way back to 15. So then what's really going on? First of all, as I travel from here to here, I am spiraling out, or I'm spiraling in because I am having my R decrease. And essentially what that means is if I draw spokes coming out, these spokes are getting shorter and shorter as my angle turns. Put that back in. Now, when I go from angle pi over 2 to this unknown angle here, whatever this unknown angle is, I have a positive radius for just a little bit. Now, I'm going to just draw a line and say this is angle alpha and this is x equals alpha. I have a positive radius at 5, but it shrinks down to 0 very quickly. And if I could severely zoom in on this, which I can only zoom in so much, I could see that as my spokes come out, they're getting shorter. And they get very quickly shorter as they get sucked into the pole. But then after I hit this angle, I'm seeing that I have a negative radius value. So I want to imagine this being a line with a negative side to it. And that line is turning, and while it turns, that negative side is also turning. And I'm sliding to the other side. And I'm looking at these negative radii kind of spoking out on the other side all the way to -5. and then symmetrying itself back in. These are all negative radii for all of these positive sides of the line while I'm traveling from alpha until I reach whatever this angle is. Then it pops back up with a positive R, and I know the values because I can plot them. So if you play around with seeing how a Cartesian graph matches up with a polar graph, you can use the language you already know. I have a question though. How comfortable do all of you feel with graphing sine and cosine? Because now that I think about the fact that you missed certain things due to the COVID time, did you spend enough time graphing sine and cosine graphs in the past?
Yeah, I think we had that unit, or at least in my class, we had that unit before, well, most of it before like COVID.
Oh, good, because that's
I don't know if it was
huge.
in other classes.
That's huge. If you are comfortable with your sine and cosine graphs, it makes a giant difference in the types of functions you're asked to deal with in polar. But regardless of what your of whatever function they give you, this, okay, if you're not that comfortable with them yet, I can also talk about that a little bit. Let me show you that regardless of setting aside your knowledge of sine and cosine, you can look at a variety of graphs. So if you go to, this is, I guess, slide 2, you can look at, if I change right here, I'm located at angle pi, and I'm looking at a positive radius growing, shrinking, and then I can look at when it goes negative and how that affects everything around it too as it's pulling at it. So what you can do is you can literally just try to mimic functions you already know a little bit. So let's see, let's do like, I'm trying to do somewhat of a parabola for a short bit of time. Yeah, this only lets me go so far. That makes it difficult. But I'm just going to flatten these out. So you can just take a look at, if I was dealing with a graph where the R was 0 and it had a negative radius, it continued to increase, but then that negative radius went back to 0, that it is drawing over here on the other side of the angles we're working with, because the angles through here are actually 0 to pi over 2 and a little bit farther. But what's being graphed is graphed on the other side, and it's always going to make a counterclockwise motion. Now, let me do a little bit with, if you're not comfortable with graphing sine and cosine. Oh, I know. I want to grab my Desmos of, I had found somewhere that somebody had created what I'm about to find you, and it is like huge. If I can find where it is. You can see I have way too many graphs and I need a way to organize them. Can I find it? I know I can find you. Where are you hiding? Oh, I have search. There we go. Okay. So what this allows you to see is it's basically explaining an angle going from 0 all the way around to 360 and showing you how sine is created. Sine is a lot easier to understand in its creation from the unit circle. So this is a unit circle, and the cosine of the angle as I turn, whoops, that isn't what I wanted to do. Okay. The cosine of the angle, why did I just say cosine? The sine of this angle that I see right here is the same as the y value of this point as I'm going around the unit circle. I actually create the graph of sine from the unit circle. And now it's funny because we're using our sine and cosine knowledge to go to something that is actually more like the unit circle, because polar graphing is just the unit circle, but any circle with any radius and having that change as we go around. But it's good to just take a look at the fact that what we know as our Cartesian graph of sine is created by just watching the y coordinate change on that unit circle as we go around. What you need to know about sine is, didn't mean to do that. What you need to know about sine is mostly these particular points. Angle 0, pi over 2 pi, 3 pi over 2, 2 pi, and the fact that it's 0, 1, 0, negative 1, and then back to 0. Knowing that is huge, essential, necessary. And then where is it? If you look at it with cosine, it's a little bit harder to see because with the cosine graph, it's following the x coordinate. While this point turns around the circle, we're actually looking at that x turning vertical. Then once you know what those two graphs are, then from there, you've got issues of multiplication. So if I multiply either of these two by a positive constant, all I'm really doing is taking the y values that I currently have and stretching them to that number. And here's what I tell people. If it is a number multiplying to the sine function or to the cosine function, you are literally taking just the y coordinates that you see and multiplying them by that number. But if you see a number multiplying to the x, you actually need to take what your x normally is and divide by that number. So for example, if I have cosine 3x and I want to graph it, then I'm not multiplying my x's by 3, I'm actually dividing my x's by 3. So when I divide this by 3, that's going to squish it in quite a bit. And now it squishes it a little bit farther. I'm not drawing this perfect, but what was 2 pi is now 2 pi over 3. What was pi is now going to be located at pi divided by 3. So a big bottom line is whatever x is multiplying by, divide all your x's by that to see how they stretch or squish. If x is being divided by a number, multiply your x's by that number. You always do the opposite operation to what is being done to x to figure out how a graph transforms, and you do the same operation for something outside the function and affecting y. So the main things you need to be able to deal with are, let's do, say, -5 multiplied by the sine of 2x. So you can start with your basic sine graph and understanding that it's 1, -1, and all the way out to 2 pi, and you've got halfway and a quarter the way through. Multiplying by -5 is going to take whatever this y value of +1 will multiply by -5 and show up down here. So it's going to turn the graph upside down and stretch it by 5 units. This y value of -1 is going to be multiplied by -5 to become a +5 and stretch up that way. So what you see here, the absolute value of that number, is your amplitude, the vertical distance from the sinusoidal axis. Then the number multiplied to your x determines the frequency. And in math, we don't really tend to focus on frequency. We focus on period, and frequency is is more of a rate, whereas period is looking at how long does it take to make a full cycle. And they always tell you to just take whatever number is there, take your normal cycle, and divide it by that number. But with any graph you have, if you take its x and multiply it by a number, it will do the opposite to all the x's you see. It will divide them by that number. So the red graph is just the stretching by -5. Then if I bring the 2 in with it, it's going to make a complete cycle while I go from 0 to pi, so it's going to go double the speed. So you want to be ready to deal with the multiplication issues outside the function and inside the function. Then you also need to be ready to work with the addition. And with this, you want to see that you have your cosine graph, but multiplied by 3 means, and you don't have to draw the perfect graph with the Cartesian. You just need to draw enough to be able to figure out what the polar graph is doing. And as I'm thinking about it, it's odd that we actually take the unit circle and stretch it into a wave, and then we focus on that. And then we try to take that wave and bring it back to a polar form several years later. It is kind of interesting. Anyway, this says move it up 2 units. I usually start by my center axis, moving that up to 2. And then moving everybody else up 2 and then letting it go. And what's really important to get out of it is knowing the length of the cycle. Cut it in half again, and then look at those quarter ends. And from there, if you want to graph the polar graph, you can start by plotting these points as polar points. X equals theta means, x equals 0 means theta equals 0, and you're at 5 units out. Then when x is pi over 2, with a y value of 2, that means you have rotated to pi over 2, and you are positive 2 units after you have made that turn. And in between here, this is showing the y value of this graph is decreasing. For the polar graph, the r value is decreasing. And it does help to draw the spokes to see these spokes getting shorter. Every time you turn just a little bit, the r is getting smaller coming out of the pole. Then we hit this angle again where it's going to be sucked into the pole and spit out as a negative angle. And this is -1, so that means that when I'm at pi radians with a -1, that actually puts me over on the positive x-axis, which is a little bit awkward. But then everything else along here is symmetry, and you can just copy what just happened the rest of the way. Now, the next thing we might want to look at is looking at Rose curves. So I'm going to give you oh, yes. Yeah, and just let me know what you need or don't need. If I'm doing something you don't need, let me know. Okay, I'm going to move over. So I'm going to take a look at, let's have fun and make it 5 theta. And I'm actually going to change this to just some number. If I were to graph the Cartesian version of this, then I find it easiest to not worry about displaying on my Cartesian graph the correct spacing, because I'm just really trying to get some plotted points ready. So the 8 on my y value is telling me to take that sine graph and stretch it so that instead of going out to 1 and -1, it goes out to 8 and -8 and vertically stretches. The multiplication by the 5 is meaning that where you would normally have 2 pi, its x-coordinate is being divided by 5. Every one of these x-coordinates is being squished toward the y-axis. And so once you know that that is 2 pi over 5, you can cut it in half again, and this gives you some of the angles that you're going to be needing when you go to draw the polar graph. Now, you're not tremendously familiar with exactly where these are, so let's kind of get a feel for this. 2 pi over 5 is 2/5. 2/5 is a little bit less than a half. If it had been 2.5, it would have made it 2 pi over 2. So what I'm trying to say is 2 pi over 5 is about here, and I'm just approximating. But another thing that I can do to save myself a little bit of time is to understand when I multiply theta by that 5, what it actually does is it takes, what am I trying to say? Hold on, let me catch my thought. What normally happened at pi is happening at pi over 5. So what I'm seeing is this bump has to go back and forth 5 times as I rotate from 0 to pi. So I've got my 0 to 1 pi over 5, my 1 pi over 5 to 2 pi over 5, my 2 pi over 5 to 3 pi over 5, 3 pi over 5 to 4 pi over 5, and then my 4 pi over 5 to 5 pi over 5, which takes me to pi. So what you can see is the split between 0 and pi is 5 equal sections. And 5 is not the ideal number, which is for some reason why I chose to use that. But we're trying to split this axis up into 5 equal sections. So 1, 2, I'm not, and I'm not doing a very good job. 1, 2, 3, 4, 5. I need Desmos. I'm doing a terrible job on drawing that. But actually, what I'm trying to do is help you to understand how to like deal with this when your calculator isn't available. Okay. Can you see that I'm approximately splitting this up into 5 equal sections? Whatever you have multiplying by that theta, you can actually, that is if you're using sine, you can split up your 0 to pi in that many sections. If this is an odd number, then when you start off with the positive radius loop, let me use, oh, let's go rainbow color. Whee! Now, the 8, all that 8 is doing is causing this to stretch out a little bit farther to an R value of 8. With it being odd, though, it goes immediately into a negative radius. So what I'm going to do is I'm going to extend the, try to do a decent job extending these lines. Okay, now let's watch Sparkle do its thing. I just created that curve, and now I'm going to go into a negative radius, and it creates that bump. Then I skip this, and I come over to the 2 pi over 5 to 3 pi over 5. I have a positive radius, and I get this loop. Then I have a negative radius when I'm about to turn through 3 pi over 5 to 4 pi over 5. So I actually graph it over here. And then I finally hit this with a positive radius. But when you're dealing with this number being odd, then once you've done your 0 to pi, what you did was positive radius, negative radius, positive radius, negative radius, positive radius. And now I'm about to go into a negative radius, which means I'm not going to graph in this region. This region is going to graph over here, even though that's already drawn. So one thing you want to know about Rose curves is if the number theta is multiplying by is odd, the rose petals only occur in every other section. If you are dealing with this being an integer, not a fractional number, then you can basically, I should add, if you're dealing with sine. Cosine has an awkward cut because cosine begins with a loop out over here. But you can take the 0 to pi, cut it up into 5 equal spaces, whatever number this is, and then extend those lines out in the bottom half. If this is an even number, every single section gets a petal. If it's an odd number, then it's every other section. And let me go ahead and grab Desmos because I have some other things that I can share with you. Let's see, which one do I want to do? So this is actually looking at a rose curve, but with fractions. And you can, this is really exciting to just let it go and play with it. All of these, now, if it looks like some of these are not fully formed, it's because I'm not giving it enough time. All of these are rose curves. You're really only expected to know how to deal with them if this is a fraction, and that's it. And let me actually, no, I don't want it to do that. Okay, never mind. If you go into your Desmos, you can actually just type in R equals, pick a trig function, and I've shown you that you can, not there, you can click on theta right here, and you can make sliders and just look at a variety of graphs that you can get. But I've got to say, I found this just before seeing you guys today, right now. So like about right before 7, I ran across this as I was searching the web for what do you have. This is possibly the most useful thing you can do, is just play with this to understand the relationship of the way you know graphs work in Cartesian and how that translates into a polar situation. If you go into multivariable calculus after this class, you need to understand polar graphing, because you're going to take that and make 3 dimensions out of it. One of the ways you're going to do that is by having the XY plane be your polar graph and then just going in a Z, like a rectangular Z away from that. But the one that's actually a little bit harder to work with uses polar as a little bit of a basis, but it then creates another radius on top of that. So you want to know your polar and how it works before you go in there. And you do have the opportunity of, you can, honestly, I think playing with this could teach you so much. Are any of you playing with this? Is it helping with? Awesome. And this whole thing is a lesson that a teacher can take an entire class through, but you can just look at it and see this is literally guiding people slowly through toward an understanding of polar graphing. And you can sit here and play with this and actually see what's going on. At a particular angle, you can have a positive radius or a negative radius. And then you can move them in all sorts of ways. Now, with a little bit of time left, is there anything in particular you could use some help with? Thinking about it, how do you feel about solving trig equations? Do you feel, as long as you don't have to go into, yeah. In fact, do you want to take a look at some of the homework that you have? Oh yeah, we can do a little bit of the study guide too. Well, the yes is, I think, to the to this. Okay. One of the places where you're going to need to do some solving is with number 6 here. Have any of you started looking at this? For number 6, you're going to need to figure out where these intersect because I didn't show you enough of the graph for you to just see where they intersect. And what you want to do is look at your 2 equations. And you're just playing a game of bring those 2 equations in as if these are the same r's and, well, there's only one theta. So basically, I can take r equals 2, plug it in here. And from there, understand your goal when you're solving trig equations is to first isolate the entire trig function. So basically, I'm going to divide by 8 before I do anything else. And the way that I like to work with it at this point is don't panic if the angle there isn't just theta. Imagine that this is angle blob and you're trying to solve for angle blob. What are the blobby angles equal to if you have a sine value of 1/2? So if you look at your unit circle, sine is asking where is y equal to 1/2 when it goes 1/2, root 2/2, root 3/2, and then up to +1. And so you want to be aware that that is π/6 and 5π/6. Now, you also want to be aware that to go from π/6 and find another point that lands on that same spot, you have to add 2π to that. In fact, if you add 2π or subtract 2π any integer number of times, that is going to give you half of your solutions to what blob angle equals. And blob angle happens to be 2 theta. The other thing that it can be equal to is 5π/6 plus any 2πn. And again, that's what the blob angle equals. So if you want to know all the values that theta could possibly be, you want to divide both sides of this equation by 2. So when I divide by 2, I'm going to get pi over 12 plus pi n. And over here, I'm going to get 5 pi over 12 plus pi n. Now, when I come back to the fact that I already have a graph here, that's going to help me to save some time. The very first angle has to be the smallest positive angle. And if you look at your possibilities, that's going to be pi over 12. This angle is going to be the next positive angle out, which is going to be 5 pi over 12. And then if you look at the idea of you're just adding pi n to get to the very next one, you can see that that makes sense just looking at this visual picture. So if I add pi n, that'll bring this to 13 pi over 12. And then if I add pi times 1, I meant with n being 1, that will get me the opposite end of this. So 7 pi over 12, if I can add right now. No, I can't add right now. 17. And so that allows you to know where all those angles are actually located. And this is really important to be able to do. And it's not the only place where I'm leaving you hanging on you need to find where these angles occur. For something like this problem, you need to know when is my r equal to 0. Solve this equation, and that's going to help you to determine where this graph is sucked into the pole and becomes a negative angle. And then also it's going to tell you where the graph finishes its negative value of r, comes back to the pole, and then pops out as a positive radius after that. Solving that equation will help you to find out what those angles are where that happens. And then here's another good one for you to see if you've got the hang of how do I solve these equations to determine exactly where they intersect. So let me just, we've got about 5 minutes left. So I'll tell you maybe when we get offline, maybe try solving that equation and find those angles, and that'll help you. Then is there anything, what was it that somebody said? A little bit of the study guide. Let me think. For what it sounds like the majority of you are asking, let me start off with, do you need any help getting started in some of these problems, any of these problems? Is there a number that you're like really stuck with? Okay. And let me forewarn you that some of these first problems are a little bit tedious, particularly 3 and 4 have some tediousness to them that I'm leaving off the test because it's too time consuming. While you're trying to take a test in an hour and show everything you know. So with number 10, you're only finding the area inside one of these loops. You can pick whatever angles you want. When you look at this graph, you should see that it looks very much like it's being spit out of the pole at angle 0. But there's another angle over here that needs to be found for where it is being sucked back into the pole. That's going to be determined if you look at the Cartesian graph. Or actually, it could be found by solving an equation. These two angles are the angles where r is equal to 0. So if you set your r equal to 0, this might actually be faster than graphing this. So realize you've got different ways you can go about it. You can graph what you know about your sine graph because of this 3, but because of this 3. You can also just realize the things that matter are what are the angles where the r is 0. That's a really key thing. So you're really looking at 3 theta is the angle. Sine gives you an answer of 0 when the input angle is 0, pi, 2 pi, and, so on. So any n times pi, where n is an integer, is going to be a solution for the angle 3 times theta. So that means when you divide by 3 and then replace n with integers, you're going to get these angles. So if I put in n equals 0, I'm getting angle 0. When I put in n equals 1, I'm actually getting pi over 3. If you're only doing one loop, you can just integrate over the sweep of an angle that creates that loop. Then bring out the formula of 1/2 r squared d theta, where r is that 3 sine 3 theta. However, there is so much symmetry to this graph. If you play around with this idea a little bit more, let's say we integrate from pi over 6 to pi over 2. If I decided that I wanted to integrate from pi over 6 to pi over 2, what would be helpful for you to see is you're getting this area with a positive radius. Then it's turning into a negative radius and drawing along here. And do you see that you're actually getting still the same area as one of those petals because you're getting a half petal, but 2 of them? So there are a lot of things, a lot of different ways that you can write this with the symmetry that's going on. So the more you play with polar, the faster you're going to get with it, and the more you're going to be able to just create through the thought process of how polar works. And I hope this helped a little bit, but I thought I'd do a session where I would give you stuff. I didn't, hold on, let me stop the recording.